Hi, so we're back at the second topic of this chapter, really talking about ionic compounds and specifically their properties. So we talked about lattice energy, and lattice energy is going to have a piece in all these other properties. So the first one we're going to be looking at is solubility. In general, ionic compounds are very soluble in water. So what does that mean? What does that word solubility mean? Well, solubility means that it will dissolve. Dissolve specifically means that it will be incorporated into a liquid in order to make a solution. And lots of different compounds will dissolve. Most ionic compounds and a good deal of covalent compounds, but not all covalent compounds. The one that is specific to ionic compounds is that ionic compounds dissolve and dissociate. What does dissociate mean? Dissociate means that the individual ions will split up from their crystal lattice, be surrounded by their water molecules, and then just really be floating throughout the solution. This picture over here does a really good job of showing that process. So in the middle, you see this is your crystal lattice, your crystal of NaCl, where positive and negatives are attracted to each other. When that gets in contact with water, we know from previous science classes that water is a very polar molecule, which means one side is partially negative. That's what it's a lowercase delta. That's what that means. So one side is partially negative. The electrons are more on that side, and the other side would be partially positive. And we know through the electrostatic force that opposite charges attract. So the partially positive end of the water molecule, which is the side with the hydrogen, will be attracted to the negative ion. So for salt, it would be the chloride or chlorine ion. And then the partially negative side of water, which is the oxygen side of water, is attracted to the positive sodium ion. So as you can kind of think of these water molecules as attacking the crystal lattice of salt and pulling those individual ions away. So eventually, when you have a solution of salt water, there's actually none of that in salt water. It's 100% dissolved and dissociated. And why do ionic compounds do that? Well, first of all, because ionic compounds are attracted to the water. They're attracted to the water and they're attracted to each other. So whichever one they're more attracted to is where they'll go. If they're more attracted to the water, then it will dissolve and dissociate. If they're not very attracted to the water, they're much more attracted to each other, it may not dissolve. The other piece of that is something that's called entropy. It means randomness or disorder, and reactions proceed. One thing that's favorable to reactions proceeding or processes proceeding is if there's an increase in entropy. We don't need to know about that now. We're going to talk way more about that in later chapters. So ionic compounds dissolve and dissociate. That's one property. Another property that we see with them is that they have very high melting and boiling points. You can see that the lowest melting point on this chart here is sodium iodide, but it still melts at over 600 degrees Celsius. There's very few ionic compounds that you could melt at your house. If you take a block of salt and put it in your oven, you won't get a high enough temperature to melt it. Whereas something like sugar, you can melt quite easily right on your stovetop. And the trends in the melting and boiling points, you may notice, are very similar to the trends we saw in lattice energy because those two things are very similar. They're related, right? So if I just highlight in pink here all of the Na, so the only thing that's differing in the three things that I highlighted in pink are the anion, the negative guy. So NaCl, NaBr, Nai. And we can see the same trend that occurred with lattice energies happens with melting points. That the smaller the ion of those three, chlorine is the smallest ion. So the smaller the ion, the closer the ions are together, the greater the attraction and the more energy it takes to overcome that attraction, because that is what melting is. Melting is when, or in order for an ionic compound to melt, you would need to partially overcome the attraction between the particles. And then the other trend that we saw with lattice energy was that the higher the charge difference, the higher the lattice energy, and we can see the same thing here, that the highest one on this side or on this page is magnesium oxide that is formed from, right? Remember, magnesium is a 2+ ion and oxygen is a 2- ion. Calcium chloride, calcium is a 2+, but chlorine is only 1-. So you can see very similarly, both factors of Coulomb's law are contributing to the changes or the differences that we see in melting point. Another really important property of ionic compounds is that they will conduct electricity, but it's an if, it's a big if, only when or if they are dissolved in water or heated till it is molten. So basically made into a liquid. Why is that? Because you need two things in order to conduct electricity. And this will be a theme that we will talk about throughout the year. The two things that you need in order to conduct electricity is you need some sort of charged particles. And these charged particles need to be free to move. So that's why ionic compounds are really good at conducting electricity, because they're totally made of charged particles. But they don't conduct electricity all the time, because only sometimes are they free to move. When are they free to move? Well, dissolved in water or molten. If you look at this picture right here, you can see the first, right, here's a light bulb. Here are the electrodes in the light bulb. The electrodes in the light bulb or in the solution, if this solution conducts electricity, then that will complete the circuit and the light bulb will light. If the two electrodes going down, if there's no electricity conducted between them, the circuit will not be complete and the light bulb will not light. So if in the first scenario, it is in distilled water. Distilled water, the particles are very free to move. But remember, what are the particles in water? H2O, molecules. Molecules have no charge. Therefore, the water will not conduct electricity. And that's true. Pure water will not conduct electricity. But rarely in real life do we ever encounter pure water, which is why it's always important to get out of a swimming pool or get out of the ocean when we see lightning, because lightning is a form of electricity, and ocean water will conduct electricity. Your bath water will conduct electricity, just not pure water. You can see in the center here, we have, it is solid, NaCl. So full of charged particles. You can see all the charged particles in there, but are they free to move? No. So therefore the light bulb doesn't light. But when I mix those two, and I have now my charged particles that are free to move, that is able to conduct electricity. All electricity really is a flow of a charge. That could be in ions, that could be electrons, but as long as a charge can flow, then that is what electricity is. So in this solution of the two, of salt and water, we do have those two different scenarios, those two cases that need to be in order for it to conduct electricity. The solution, it does contain charged particles, and those charged particles are free to move. This picture here is showing the exact same thing happening, but now what those two electrodes are placed in is not solid salt, but molten salt. Molten is the word that we use for the liquid form of something that is not a liquid at room temperature. So we would say molten salt, not really the word liquid salt, although we would use the word liquid to describe water, liquid water. Very similar to the word gaseous and vapor. Right? We use oxygen gas. We don't say oxygen vapor. We say water vapor, because vapor is our way to say this isn't a gas at room temperature, but I have heated it, so it is a gas. Molten is our way of saying this isn't a liquid at room temperature, but we've heated it so that it is a liquid. When I heat sodium chloride. When I heat salt, I do give those particles, the ions, enough energy so that they are free to move. And because now we have charged particles that are free to move, we can see that the current meter does have a reading. The light bulb would light. There is a flow of electricity. And then the last property of ionic compounds is that they are hard and brittle. What we mean by that, so what's like the opposite of something being hard and brittle? Well, the opposite of hard would be something that is soft. Some metals would be considered soft. All metals are considered malleable. Malleable is the opposite to brittle. If you think about taking, when we were talking about the properties of metals, if we hit a metal with a hammer, we would see that the metal flattens out. And that is due to the specific structure of what's going on in a metal. But with an ionic compound, if I were to, hit an ionic compound, so like the big salt block in the front of my classroom, or just any piece of salt, especially if you have like rock salt at home for your driveway, you might see larger chunks of it. If you were to hit that with a hammer, all you need to do is move it so that a positive ion is directly next to another positive ion. And what that will do is cause now electrostatic, instead of attraction, it would now be electrostatic repulsion. Those ions would fly apart and it would shatter like glass, basically. Glass is something really interesting that we have not talked about yet, but it would sort of have that same effect. So ionic compounds are soluble in water. When they're in water or molten, they will conduct electricity, and they are hard and brittle. They have high melting points. We can describe them using something called lattice energy and melting points and lattice energy. And actually, most of these properties are affected by how strong that attraction is between the ions, which is ruled by Coulomb's law.